It is the early hours of October 24th, 1942, somewhere in the sand west of El Alamein. The desert is black and silent, save for the distant thump of artillery rolling across the dunes like far-off thunder. Ahead of a column of British infantry lies a stretch of ground that looks, to the naked eye, entirely unremarkable. It is not. Rommel's engineers have spent months turning this patch of desert into what German soldiers themselves have nicknamed a Devil's Garden, a belt of buried explosives up to 5 miles deep, sown with hundreds of thousands of anti-tank and anti-personnel mines. Somewhere in that darkness, a strange machine grinds forward on tank tracks, a great rotating drum mounted on arms in front of its hull, dozens of heavy chains thrashing the earth in a deafening, rhythmic frenzy. Dust and sand erupt in a filthy brown curtain. Every so often the drumbeat of chain on soil is interrupted by a sharper crack, an explosion, as a buried mine detonates harmlessly beneath the flailing steel instead of beneath a soldier's boot. The men following behind watch this ungainly contraption clear a path through certain death, and they have a name for it, too. They call it the Scorpion. What almost none of them know, as they walk that narrow, cleared lane to relative safety, is that the machine which is saving their lives did not begin in a military laboratory or a government design office. It began, according to several accounts, in the mind of a farmer. To understand why that mattered, you first have to understand the scale of the problem the Allies faced in North Africa, and it was staggering. By the autumn of 1942, mine warfare had become one of the defining features of desert combat. The North African campaign was fought across vast, largely featureless terrain where there were few natural obstacles. No rivers, no forests, no hedgerows to slow an advancing army. Mines filled that gap. German and Italian forces laid them by the hundreds of thousands, often in dense, overlapping patterns designed to funnel attacking tanks and infantry into pre-registered killing zones covered by anti-tank guns and machine gun nests. Some estimates place the number of mines laid in the Alamein defensive belt alone at close to 500,000. Clearing them, prior to any mechanical solution, meant sending sappers forward on their stomachs in the dark, probing the sand inch by inch with a bayonet or length of wire, feeling for the telltale resistance of a buried teller mine. It was agonizingly slow work. A skilled team might clear only a few dozen meters of lane in an entire night under fire, with the constant risk that a single mistake, a mine triggered by a probe at the wrong angle, would kill or maim the man doing the searching. Armored formations, meanwhile, needed cleared lanes wide enough and fast enough to exploit a breakthrough before the enemy could reposition, and manual clearance simply could not keep pace with the tempo that mechanized warfare demanded. Existing mechanical attempts to solve the problem had largely failed. Rollers pushed ahead of tanks were heavy, cumbersome, and prone to detonating mines directly beneath the vehicle towing them, destroying the very tank they were meant to protect. Improvised plows struggled in loose desert sand, which simply flowed back over the blade. What the British desperately needed was a machine that could detonate mines at a safe distance from the vehicle clearing them, that could operate at something approaching walking pace across open desert, and that could be produced quickly, using parts and workshops already available in theater rather than waiting months for factories back home to tool up for an entirely new design. It seemed, to many of the engineers wrestling with the problem, close to impossible. There was also a deeper, more human dimension to the crisis, one that rarely made it into official dispatches but weighed heavily on commanders all the same. Every hour spent clearing a lane by hand was an hour in which the attacking force lost the element of surprise, an hour in which the enemy could reinforce, reposition artillery, or simply wait for daylight to bring devastating direct fire down on troops still pinned in the open. Casualty rates among the sappers tasked with manual clearance were grim, and the psychological toll of that work. Inching forward in silence, aware that a single misjudged probe could be the last movement a man ever made, was recognized even at the time as a burden. Few other roles in the army demanded. Some units reported that morale among mine clearance parties suffered more acutely than in almost any other branch of combat engineering, not because the work was any less brave than an infantry assault, but because it offered no opportunity to fight back, only to endure. Any mechanical alternative, however crude, that could remove even a portion of that burden from human hands was going to be seized upon eagerly by commanders desperate to keep their timetables and their soldiers intact. The idea that eventually broke the deadlock is credited, in most accounts, to Abraham du Toit, a South African transport officer and, before the war, a farmer, who reportedly proposed a strikingly simple mechanical principle: a rapidly rotating drum fitted with lengths of chain, striking the ground ahead of and slightly beneath a vehicle's path with enough force to trigger any buried mine before the vehicle itself reached that ground. The image, often used to explain the inspiration behind it, whether apocryphal or not, is one of an agricultural threshing drum, the sort of rotating, flailing mechanism used for generations to beat grain loose from its husks, repurposed here to beat death out of the sand instead. Du Toit's concept was taken up and developed with South African engineering support in Egypt, and from there passed to British military engineers who set about turning a promising idea into a working weapon of war. There is, it should be said, some genuine murkiness in the historical record about exactly how Du Toit's idea traveled from a farmer's observation to a formal engineering project, and different accounts assign varying degrees of credit to the South African engineers, the British officers who championed the concept once it reached them, and Du Toit himself. What most versions of the story agree on is the essential shape of it. An outsider to formal military engineering, drawing on an entirely civilian, agricultural frame of reference, proposed a solution that professional military minds, thinking in terms of armor and ballistics rather than threshing and harvesting, had simply not considered. It is the kind of origin story that sounds almost too neat for a war defined more often by grinding industrial effort than by flashes of individual inspiration, and for that reason it is worth treating with a degree of healthy skepticism even as it is recounted, since wartime anecdotes have a habit of sharpening into legend with each retelling. Whatever the precise chain of individual contributions, the task of turning the idea into a working weapon fell to workshops in Egypt, working with what was available. A Matilda II infantry tank, already in service and slow but heavily armored, was chosen as the base vehicle, since its thick armor offered the crew reasonable protection from the mine blasts the machine was, by design, going to be triggering constantly. Mounted on two arms projecting forward from the hull was a steel drum roughly the width of the tank itself, driven not by the tank's main engine, but, in several early versions, by an auxiliary engine bolted to the outside of the hull, because diverting power from the tank's own transmission proved impractical. Attached around the drum's circumference were dozens of short lengths of heavy chain, each tipped with a small weight so that as the drum spun, at speeds that could exceed 100 revolutions per minute, the chains whipped outward and downward with tremendous force, hammering the soil ahead of the tank to a depth of several inches, enough to set off a pressure-sensitive mine, but not so deep as to bury the drum itself. The noise, by every surviving account, was extraordinary, a continuous, bone-shaking clatter not unlike a road drill striking concrete, audible from a considerable distance and accompanied by a rolling wall of dust that, while useful for concealment, also left the crew almost completely blind to what lay immediately ahead. The finished machine, christened the Scorpion, weighed several tons more than a standard Matilda, moved at little more than walking pace when flailing, roughly 1.5 miles per hour, and needed a second crewman simply to manage the auxiliary flail engine in addition to the tank's normal crew. Production, given the improvised nature of the project and the urgency of the desert campaign, was never large in these early Egyptian-built batches, and precise numbers remain difficult to pin down with certainty, since many of the workshop records from this period were never centrally archived. What is clear is that by the time of the Second Battle of El Alamein, enough Scorpions existed to be organized into small specialist troops attached to the assaulting divisions, tasked with the singular, nerve-shredding job of clearing lanes through the Devil's Gardens ahead of the main armored thrust. The manufacturing effort behind the Scorpion also deserves a moment's attention, precisely because it was so unlike the tidy, purpose-built production lines that people often imagine when they picture wartime weapons manufacture. There was no dedicated factory, no assembly line stamping out identical hulls. Instead, workshops attached to the Middle East Command, staffed by a mixture of British and South African engineers and mechanics, essentially hand-built each conversion using whatever Matilda hulls could be spared from frontline service, whatever spare engines could be sourced from damaged or written-off vehicles, and chain stock that in some cases appears to have been repurposed from entirely unrelated equipment. This improvised approach meant that early Scorpions were not perfectly uniform machines, and mechanical reliability suffered accordingly, with the auxiliary Flail engines in particular proving a persistent weak point, prone to overheating and choking on the dust their own drums threw into the air. Their combat debut at Alamein was, by most accounts, a mixed one. Several Scorpions broke down under the punishing strain the flailing mechanism placed on their improvised auxiliary engines, choked by the very dust clouds they generated, and more than one became a target for German anti-tank guns the moment its noise and dust betrayed its position. Yet, where they worked dramatically. Lanes that would once have taken engineering parties an entire night of crawling, probing labor to clear could, under favorable conditions, be opened in a fraction of that time, and infantry and armor that followed behind the flailing drums did so with a confidence that manual clearance alone could rarely provide. Battlefield reports from the Alamein sector describe engineers and infantry alike watching the machines with a mixture of awe and disbelief, some soldiers later recalling that the sheer noise of a Scorpion at work was, in its own strange way, almost reassuring, proof that the ground ahead was being cleared rather than merely hoped to be safe. Exact figures for how many mines any individual Scorpion detonated in a single action are, unsurprisingly, not reliably recorded, and some of the more dramatic claims made after the war likely owe as much to legend as to logbook. What survives more reliably in the historical record is the broader pattern, that Flail clearance, however imperfect in its first outing, had proven the underlying principle sound enough to warrant serious, sustained development for the rest of the war. If you are finding this interesting, a quick subscribe helps more than you know, and there is a great deal more to this story still to come. Germany, for its part, never developed an equivalent mine flail vehicle on anything like the same scale, relying instead through most of the war on manual clearance by combat engineers, sometimes supplemented by simple rollers such as the Rommel S, a heavy tracked roller vehicle that pushed weighted wheels ahead of it to crush mines, an approach that worked but offered nothing like the speed or flexibility of a flail. The Americans, facing their own mine problems after entering the North African and later European campaigns, experimented with a rather more brute force solution nicknamed Aunt Jemima, a colossal set of concrete-filled rollers mounted ahead of a Sherman tank, an approach that proved so heavy and unwieldy and so prone to becoming stuck or throwing tracks that it saw only very limited operational use before being largely abandoned. By contrast, the British flail concept was refined rather than discarded, evolving through several iterations after North Africa, culminating in the Sherman Crab, which married the flailing drum to the more mechanically reliable and widely available Sherman tank chassis, with the flail now driven directly from the tank's own engine rather than a bolted-on auxiliary, solving one of the Scorpion's most persistent weaknesses. The Crab could switch between flailing and normal driving far more readily than its predecessor, and it was Crabs, not Scorpions, that would go on to play one of the most significant roles of the entire war on the beaches of Normandy in June 1944, clearing lanes through German beach minefields under fire as a part of the specialized armored formations known collectively and rather fondly as Hobart's Funnies, after Major General Percy Hobart, who oversaw their development and deployment with the 79th Armored Division. Where German defenders had mined the approaches to the invasion beaches heavily, Anticipating exactly the kind of manual clearance delays that had slowed Allied progress in the desert, crabs instead flailed paths inland at a walking pace under direct enemy fire, allowing following armor and infantry to move off the beaches far faster than static defense planning had assumed possible. The comparative advantage by this stage of the war was stark. Where German forces still relied overwhelmingly on manpower and improvised rollers to deal with minefields, and where the American concrete roller approach had proven itself impractical for widespread use, the British Flail, refined over 2 years of hard operational lessons from a rough Egyptian workshop prototype into a reliable engine-driven system fitted to a proven tank chassis, had become the most effective mechanical mine clearance solution fielded by any major combatant in the war. The material impact of the Flail tanks is, in truth, difficult to state with precise statistical certainty since so much depends on individual actions that were never comprehensively logged, and historians continue to debate exactly how many lives were saved that would otherwise have been lost to manual clearance delays or mine strikes. What is far less contested is the psychological and operational impact. Commanders who had once been forced to build entire assault timetables around the painfully slow pace of manual mine clearance could, from Normandy onward, factor mechanical flail clearance into their planning with genuine confidence, compressing timetables that had previously assumed hours of exposed, crawling work into a matter of minutes for each cleared lane. The concept did not end with the war either. Flail-based mine clearance refined further through the post-war decades remains in active use today, and modern armies including the British Army still field engineering vehicles that use variants of the same essential rotating chain principle first improvised in an Egyptian workshop from a farmer's suggestion. Surviving examples of both the Scorpion and the Sherman Crab can today be seen at the Tank Museum in Bovington, Dorset, where visitors can stand beside the very drum and chain arrangement that once beat a path through Rommel's Devil's Gardens, and appreciate, in a way photographs alone cannot quite convey, just how crude, loud, and improvised the machine that changed mine warfare really was. Museum visitors often remark on how small and mechanically unsophisticated the drum assembly looks up close, a reminder that revolutionary battlefield solutions rarely arrive looking as polished as hindsight tends to make them appear, and that the gap between a rough workshop improvisation and a war-winning piece of equipment can, in the right circumstances, be closed in a matter of months rather than years. It began, as far as the surviving accounts can tell us, not with a general or an engineer in a design bureau, but with a farmer's understanding of how a beating drum could separate grain from chaff, turned instead toward separating soldiers from certain death. It was built in desert workshops with whatever steel, chain, and spare engines could be scavenged, not in some pristine factory, but in the middle of a live campaign, under time pressure that left no room for elegant solutions. It was loud, it was crude, it broke down constantly, and in its earliest form it very nearly failed altogether. And yet, for all of that, it worked. It cleared lanes through minefields that had been designed specifically to be uncrossable. At Alamein first, then across the beaches of Normandy 2 years later, saving time that meant momentum, and momentum that, in more than one action, meant the difference between an assault that stalled under fire and one that broke through. What began as one man's rough idea about beating the ground with chains became, by 1944, one of the quiet, unglamorous engineering solutions without which the invasion of occupied Europe would have been measured in a far higher cost of lives. It is rarely the tanks that fired the most dramatic shots, or the aircraft that flew the most famous sorties, that decide whether an army can move forward at all. Sometimes it is the ugly, deafening, dust-choked machine, grinding along at little more than walking pace, doing the unglamorous work of proving that the ground ahead is safe. The Scorpion and the Crab were never designed to kill an enemy soldier. They were designed to let thousands of Allied soldiers keep walking forward instead of being carried back. That, in the end, is the entire extraordinary story of a farmer's idea, a beating drum, and a war that was in no small part one cleared meter of sand at a time.